All right, so we are still on Unit 1.D, and if you think back on SOCs, so our how we're going to describe quantitative data, we talked about the shape, we talked about the center, so finding mean or median, and today we're going to talk about the last S, which is spread. So spread and variability are the two words that you're going to see often, and they're going to mean the same thing. So the least likely way to talk about variability is the range. And so what this says is there's several ways to measure variability. And let me step back a minute and talk about what variability really is. So let's say we've got this data and our mean of the data is right here. We're going to have data that goes this direction, we're going to have data that goes this direction, and what we want to know is what is this spread in the data. So what is this spread? What is the variability? So when we talk about spread, we're talking about the difference from the mean, so from our X bar to, let's say, this value, or from our mean to this value. So our variability or our spread is always based on whatever our mean is, or our median, depending on what our center is, okay? So the simplest way that we can talk about our spread is the range. And we've already done this once before, but if you remember, our range is the max value and our minimum value, and it's the difference between those two. So the range is the max minus the min, and it is a single number. You can write the whole thing down. You can write it as a formula. In fact, let's just show you right here. So in recent years, Consumer Reports reviewed and rated 14 different midsize SUVs. Here, the distances, each vehicle needed to come to a complete stop at 60 miles per hour. So here are all of the different things. And if we want to find the range of the distribution, we want to find our smallest number and our biggest number. So it looks like 126, it looks like this is going to be my min. This is my smallest number. And 149 is going to be my max. So when we talk about the range, we can write this as 149 minus 126, but the number that we care about is this number. And because we have a formula here, we have a unit, and this is going to be miles. So you can show the whole thing, but if you report just the number is 23. All right, so the question is range a resistant measure of variability? So if you remember, resistance means we don't care about any outliers. So no, because we're looking at range as the max minus the min, then absolutely it depends. So it is not resistant because it depends on the endpoints. All right, so why is range not an ideal way of measuring variability? Well, if you think back on what I said variability is a distance from the mean. And all the range tells us is the distance between the max and the min. So why is the range not an ideal way? So we tend to not know the variance, and the variance is the variability. So we tend to not know the variance from the center. Could be mean, could be median, but what we don't know is the variance from the center, and that's really what we're looking for. So there are two ways that we're going to look at this, and this first one is going to be standard deviation. And the standard deviation, if we summarize the center of the distribution with a mean, so that's our X bar, then we should always use standard deviation to describe our variation. So standard deviation is going to describe the variation when we know the mean. All right, so the standard deviation measures the typical distance of values in a distribution from the mean, and it is calculated by finding an average distance of the squared deviations of the individual data values from the mean and then taking the square root. Now, that is a lot of words on there. And so let's talk about what this formula looks like. So the symbol that uses sample standard deviation is going to be a small s. Now, remember, a sample, with this sample, this is coming from a statistic. So it's coming from known data points. It's not our population standard deviation. That's something else. So if we have the sample standard deviation, then our formula is going to look like this. Standard deviation is going to be the square root, that's where we have the square root, of the sum of our value minus our mean squared. Now, we have our first data point minus the mean. And then we have our second data point minus the mean squared. And then it goes on and on and on. So you capture all of your data points. And all of this, still under the square root here, is over n minus 1. Now, this formula right here is on your formula sheet. So it's important that you understand all of these different terms. So if we have data, we're going to do an example problem in just a minute. But if you have your first sample minus your calculated mean and the whole thing is squared, plus the second sample minus the calculated mean and the whole thing is squared, and you add all those up and you divide by 1 minus the sample, and you take the square root, this gives you your standard deviation. All right, we'll practice that in a minute so you can see how it all goes in. But realistically, I'm going to show you how to do this longhand, and then you're never going to do it this way. You can just plug it right into the calculator. Okay, so what is the value obtained before taking the square root of the standard deviation? So if you look at this, standard deviation is this whole thing, and the whole thing is under our square root. Now, before we take the square root, that is called something else, and that is called the variance. So our variance is going to be, and you don't have to write this down, I'm just showing you what I'm talking about. That's what the variance is. So it's everything that's not under the square root. Okay, and the symbol for variance is going to be standard deviation squared. So let's go back to this. If we look at this formula, if we want to isolate this radical, get rid of the radical, we would square both sides. All right, so it makes sense from an algebra standpoint. Our symbol of s squared, which is the standard deviation squared, is the variance. So how do we calculate that? Well, I just talked about all of this, but what you're going to do is you're going to use Desmos and 1-var stats to get your standard deviation. All right, so let's practice this one time, and then I'm going to show you how to do it in the calculator. Okay, so loose granular material like sand or asphalt is piled on the ground, and the side of the piles form an angle with the ground called the angle of repose. Each material has its own angle of repose. The angle in degrees for 6 randomly selected materials are shown below. So here's what we have. Calculate the sample standard deviation and interpret this value. So I have 1, 2, 3, 4, 5, 6 different types of samples here. Okay, so what I can do is I can calculate my x bar, and my x bar is the average, and that would be 33 plus 45 plus everything up to 30, and we're going to divide this whole thing by 6. So what I'm going to do is I'm going to plug this in my calculator right here. So I'm going to go to Stat, and then I'm going to go to Edit. I'm going to clear this, and I'm going to put these numbers in. So 33, 45, 28, 50, 45, and 30. So those are my 6 data points. And then I go back to Stat, Calc, 1-vars. It's my list 1. And when I run this, I get my x bar. So my x bar is 38.5. Now, this value here is 38.5. Now, if I was to add all of these up, 33 plus 45, so all I'm doing here is adding these up. And now I divide this by our 6. I get the number 38.5. So from your formula sheet, from your calculator, you can add up all of these, divide by 6. That gives you your mean, your x bar, which is your mean, or from 1-var stats, which is the fast way to do it, you're going to get this value of 38.5. So now what we want, and we have to do this part first. because we need X bar in our standard deviation formula. So now we have our standard deviation, and this is what it looks like. I'm going to write this down, and then we're going to go straight to the calculator. So my first sample is 33. So I have 33 minus 38.5. This is my mean. The whole thing is squared, and then I'm going to add the next one. And so it's going to be 45 minus 38.5 squared plus the next one. And you go all the way up to this last one, so dot, 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 30 minus 38.5 squared. Now this whole thing is going to be over 6 minus 1. So if we look back at our formula, I have my first sample minus my mean squared plus my second one all over my total sample size, which is 6 minus 1. So this is what this looks like. So now, let me just go back and run this. All right, it gives me this value, S sub x. Now, this value here, S sub x, is our standard deviation of this sample, and it says it's 9.268. So my standard deviation here is 9.268. Now, I have to have a unit. In fact, up here I have to have a unit as well, and this is going to be degrees. Same thing here. This should be degrees. So my standard deviation is 9.268. So now let's talk about what this means. This is the interpret part. So what did we just do? What this means is the angle of repose, which is what we're talking about here, for these materials typically varies by 9.268 degrees from the mean. That is a perfect definition. Here's what you have to have. Typically varies. This is what standard deviation is. It's the variation. We want to use this word typically. So it typically varies by 9.268. That was our calculated. From what? From the mean. And you could even say from the mean of 38.5 degrees. Okay? Know this interpretation statement. So here's our context. Typically varies is what we need to have by whatever that standard deviation is. Okay, so the notation of S, lowercase s, refers to a standard deviation of a sample. And that's what we just had. We had these different samples. It says here there's 100 materials. They picked 6 of them. From these 6 samples, we have this standard deviation. So if we have the standard deviation of a population, so standard deviation of all 100 materials, we use this sigma. And this sigma is the Greek sigma that's here. It is shown on your calculator here as sigma sub x. Now, because this data is all based on just these 6 data points, then we don't know the actual value. So this value of 8.46, this population standard deviation would change if I had a larger sample. So it tells me here my sample size, n equals 6, but if n equals 66, then this number would be different, okay? So because of that, we use the sample statistic, so we're going to use just S to estimate our population parameter of sigma. So this value here of 8.46 is an estimate of the population parameter. We are almost always going to just report S because S is the data that we actually have. Okay? All right, so let's keep going here. So properties of standard deviation. So what is the smallest value of standard deviation that you can have? And the answer to this is going to be 0. And so under what circumstances will the distribution have a standard deviation of 0? Well, if I took all of these samples and my angle was 33, 33, 33, 33, 33, then in every one of these cases, my standard deviation here is going to be 0 because there's no variation from the mean. So this happens if we have a sample set is all the same number. So if I had something like 33, 33, 33, that sample set is all the same number. So that tells me that my standard deviation is going to be 0 because all of my values are the same. Okay? All right, so what we know is that the greater the variation means that we have a larger value of S. So let me draw a little picture here. So I have a histogram, and let's say my histogram looks like this. Okay, and from this histogram, I know that my mean is going to be in here. So my X bar is going to be here in the middle somewhere. Okay, and now I have another distribution that's going to look like this. So now my mean is going to be in here somewhere. Okay, and so because of that, and maybe it's more on more this direction, right? So here, if I look at this distance, and then I look at this distance is much larger. So I have a larger variation from the mean. So the more spread out the data is, the larger your standard deviation is. You want something that's tight. You want a standard deviation of 0 because that means there's very little variance from the mean. Okay? So when the mean is chosen to describe the center of distribution, which should be used to describe the variability. So if your center equals mean, then your S should be your standard deviation. And let me write this. So C here is our center, and this S is going to be our spread. So when we use mean, we use standard deviation. Now, if we have outliers, then remember, we're not going to use our center is not going to be the mean. Our center is going to be the median. So that's what this says. What measure of variability avoids impact to extreme values? Now we're going to use something called the interquartile range. Okay, and we use this if we have extreme values, and remember, extreme values are going to be outliers or data that's more spread out, right? Okay, so what we have here are quartiles, and if you think about a quartile or a quarter, then you should automatically think 25, right? A quarter is 25, a quart is 25, there's 4 quarts in a gallon, so quartile is 25. So the quartile of a distribution divide an ordered data set into 4 groups having roughly the same number of values. So to find the quartile, we're going to arrange the data left to right from smallest to largest to find the median. So when we're dealing with extreme values, we know we use the median. So with the median comes the IQR, the interquartile range. So the first quartile is what is on the left of the median. The third quartile, now notice this is not a typo, this is the third quartile, is what is to the right of the median. So the quartiles can be used to help describe the position of an individual data value within our quartiles, so within our data set. So the IQR, and that's what we call it, interquartile range, is the distance between Q1 and Q3. All right, so here's my formula. IQR equals Q3 minus Q1. Now, this is a whole bunch of stuff, and you're like, what is Q1, what is Q3, what is all of this? Let me draw this out, and then we'll talk about it. So not today. What we're talking about today is just this concept of an IQR. So what I have is I'm going to use a box plot. And within my box plot, I'm going to have some minimum value. And then I'm going to have what I call this is my Q1 value. This is going to be my Q3 value. And this is going to be my max value. Now, this line that's here in the middle, this is my median. Okay, so let me break this out a little bit more. So this is 100% of our data, our lowest value, our median, our upper value. So this is 25% of all of the data, and this is 25%, and this is 25%, and this is 25%. So this shape of this data in this box plot accompanies all 100% of our data. This part right here is our IQR, and that is the middle 50% of the data. So we have 25%, this is the middle 50%, and this is 25%. So all we care about in the IQR is this value, which is Q1, and this value, Q3. And if you really think about it, if you're going left to right, we would say this is Q1. We don't do this. I'm going to write this down just for description here, but this is the median. This is the median. But technically, it's Q2. We don't write this as Q2. But really what it is we've got the first 25%, the second 25%, the third 25%, and then technically this over here is Q4, the last 25%. Okay? So this is the concept of IQR only it only accounts for the middle 50%. So the IQR, interquartile range, so this is IQR, is the range or the middle half of the distribution. So it's just the range of the middle half, and this is the middle half that's right here. All right, so we're going to spend a whole lesson on just box plots. So let's do a little example here. So I have this data. It says catamarans are boats built with two hulls. They're very stable. Certain catamarans are built to withstand rough passage across open oceans. One important characteristic is their freshwater capacity measured in gallons to accommodate daily use of water on board. So here are freshwater capacities of a sample of 19 ocean-going catamarans. Find the IQR. Okay? So what I need here when I do this is I'm going to do the same thing that I've done before. Now, I could technically put together a number line and I could put all my values on here, and then I could calculate the first 25%, the middle 50%, I could find my median. There's no reason to do that. Just go straight to the calculator. Okay, so I'm going to go to Stat. I'm going to go to Edit. I am going to go in here and clear this and enter my new data. So go ahead and do that real quick. Oops. Okay, so lots of data, and I did that quick, so hopefully I typed that in right. So IQR, we're going to go back to our 1vars stat. So I go back to stat, calculate 1vars, my list one still. Here's the data. So this tells me my mean of 174. Now when I scroll down, it gives me my standard deviation, but I don't want to use standard deviation because I have an outlier. Now, how do I know I have an outlier? Well, I see this 79 right here, which probably tells me, oh, I got two 79s. Maybe those aren't outliers. Well, this tells us to use an IQR. So we're going to use an IQR. So here's what we're going to do. We're going to scroll down, and what you see here is you see your minimum value, you see your Q1, your median, your Q3, and your max. So if I go back to this, just to kind of show you what this would look like, my minimum value here would be 79. My Q1 value would be 145. My median value would be 158.5. My Q3 value is 206, and my max value is 360. So that's how those numbers would play out on this box plot. But in this case, if I want to find the IQR, I know that that is Q3 minus Q1. So I'm going to go straight to my calculator, and Q3 is 206, and Q1 is 145. So if I look at that, that's 61. 61 what? 61 gallons of water. So what is this saying? So now we're going to interpret what we just found. So what we just have here is the middle half of, now here's my context, water consumption on a sample of catamarans has a range, because that's what IQR is a range of 61 gallons of water. Okay, let's finish this up here. So the quartiles, that's what this is, quartiles, and the interquartile range are resistant because they are not affected by a few extreme values. So if we've got extreme values that are on the ends, the IQR is taking an average of the middle half. So if we've got individual data, it's not going to play a part. If you remember our formula here for mean, we take every single one of these values and we're going to add them up. Here, all we're doing is we're taking the middle half of the data. So what's happening out on the outsides is not going to be as important. Okay? So caution, be sure to leave out the median if you locate the quartiles. So if you just have data, can't think of a time when you wouldn't use your calculator for this, but if you do, the median is not one of the values that you're looking for. Okay? You're looking for what's happening at Q1 and what's happening here at Q3. These are the only two that we care about. We don't care about what's happening at the median. All right, so how do you know? This is what we just talked about. So which measures of center and variability are resistant? And that is going to be your median and your IQR. So which center of variability are affected by outliers? So affected by outliers, what's going to be affected is mean and standard deviation. So if you have this, if you have outliers, you're going to use your median and your IQR. So you want to use these. Okay, so we use the range to measure variability only as a last resort. And we talked about that before. I mean, initially it's easy to say, here's the range, but we don't really want to use that because it doesn't tell us how far our data is from center. Okay, so when a distribution is skewed or has outliers, which measure of center and variability should you use? Median and IQR. Let me just write this down. Median and IQR. We're going to beat that horse down because it's super important. All right. And same thing here. When it's roughly symmetric and does not have outliers, we're going to use mean and standard deviation. So we have this problem here. It says, according to estimates, approximately 20,000 black bears live in Pennsylvania. Here are the summary statistics and relative frequency histogram of the lengths in inches of a sample of 97 Pennsylvania black bears. So this is a histogram, so we don't know where all the data lies individually, but you can see that the majority of our black bears are going to be right in here, right at 55 to 65 inches in length. Okay, so here is an output, the same output you would see on your calculator. So we have 97 bears, that's what N is. Here's the mean and the standard deviation. Here's your median, and you can calculate your IQR. So how do we know which one of these to use? Your calculator will always give you mean and standard deviation. It'll always give you median and Q1 and Q3. So in this case, we have to look at our distribution. So what I'm going to say here, I'm going to just write down here where I have more space. I would say the distribution of black bears in Pennsylvania is, I would say this is unimodal and roughly symmetric. So we will use mean and standard deviation. Okay, so our mean, our X bar is 60.413, and this is going to be inches. And I know this because I have to go over here and look at my graph. And that's going to be, oh, inches, put that right here. And then my standard deviation, my S, is going to be 10.026, and this is also going to be inches. And if I want to interpret this, what I'm going to say is the typical variability in black bear length is 10.026 inches from the mean of 60.413 inches. So if I'm going to just define my standard deviation, the typical variability in black bear length is 10.026 inches from the mean of 60.413 inches. All right, that's it.